Welcome back, everybody. Sorry for the slight delay. I was looking at our schedule. Um, and I'll send an email to this effect. I know today we have exam number 2, dealing with chapters 4 through 6, I believe. Yeah, 4 through 6. Let me double check. 4 through 6. I- we can start this section here with any questions if you have anything. I was considering moving that over to one more week, to the following week. What's your opinion on that? Instead of having to do today, move it to next Wednesday.
I'm up for taking it today.
Okay. All right. All right. Well, any other comments, or we just leave it at today?
Yeah, either or doesn't really matter.
Okay. All right then. Yeah.
I was gonna say I wouldn't mind, yeah, either or, honestly.
Well, I'll leave it for today then, and then we just stay on schedule. We also have this week, which is going to be an open week as far as the lab is concerned. And again, I'll send an email to that effect. I'm trying to find the online lab that I want to use. It'll be an online lab on on Friday, which means that you're more than welcome. I will be there, okay, because I'll be there. But since it's online, it's not necessary to do the lab there. If you don't want, we do have computers there. You're more than welcome to do it there during our regular time, or do it at home whenever you feel you can get to it. But I will be there, and I'll be open for any questions or comments, or you need some, more information on a particular topic. It's basically a big open study session in the lab. Okay. So I'll send an email out to that effect.
For the online lab, do we have like an assignment to do, or is it just like a study session?
Well, there'll be a series of like videos to view, and then there'll be a series of questions based on what you view. It'll be an experiment that someone is doing, and you observe what the experiment does, and there'll be a few questions about that experiment. Okay, no different than what you do in person, other than obviously you're not doing the actual experiment. Someone else is doing it, and you're viewing it through the video.
If we have questions, is it going to be like a live thing where like you could help like answer them, or
Yeah. What I can do is, since that day I'll still be on campus, I can open up my Zoom, and if you don't want to come in, like I said, you can either do it at the lab because we have computers there, or you can do it at home. And that's a good question. I'll open up the Zoom so that if there's any questions, you can, go through the Zoom and ask a question. Would that help?
yeah, I think I'll take it at home. But if you're going to be like around for like
Yeah.
answers, that'd be
Yeah.
good.
And like I said, I'll clarify everything later today, and I'll send an email to everyone. I think Manny Goetz, you just came in. What I was stating is this Friday we have scheduled to be announced, and so what it is going to be an online lab, and so you can do it at home or you can do it on campus. And then I will open up the Zoom, so in case there's any questions, you can drop by Zoom and ask a question, and we can go through it. Okay. All right. So it's basically you look at the videos, look at the experiments that are being done by the person, and then answer a series of questions, and there you go. Okay. All right. Any other questions?
I had one more question.
Sure.
Noticed it wasn't on the homework, but I was just double checking to make sure it's not on the test. But on one of the practice problems, I think it was chapter 6, it asks to like draw Lewis dot structures,
Mhm.
but we didn't like learn that. That's not going to be on the test or anything, right?
Well, as far as Lewis dot structures,
Yeah, I didn't like learn that in any of the lectures or anything. So
well, that should be chapter 7.
oh,
Yeah, which is the one I'll probably be jumping into if there are any questions, but the exam itself is chapters 4 through 6.
oh, okay. Well, I think there was one question like on chapter 6, but I guess I won't worry about that.
Because in chapter 7, I introduced about Lewis structures and for the atoms and for compounds, and then from the Lewis structures, be able to determine geometry, and that's all chapter 7.
Okay.
Okay, and that won't be no tests on that until after spring break, which is really not too far away. It's like what 2 weeks, 3 weeks from today. 1, 2, 3 weeks from today. Okay. So, but if you see that question, if you know specifically, send me an email, or if you see it now, you want to share it, and we can try to answer your question.
Yeah, I was just making sure it wasn't on the test because I was like, I don't remember that.
Yeah, that Lewis dot structures is all totally chapter 7. Because 6 was 6 dealt with the periodic table. Okay. 5 dealt with the atomic structure and the electronic configuration. And then 4 dealt with atoms. So 4 is atoms, 5 is atomic structure, and 6 is again the periodic table, which was a fairly short chapter. Okay. And then 7, 8, and 9, which is the next one, is chemical bonding. We're going to talk about chemical bonding. And then nomenclature, we get to name compounds. And then 8, 9 deals with acid and bases. Okay. Any other questions? Pardon me 1 minute. All right, my apologies. My little one just came back from the dentist. She was all excited to show me what she got, other than potential cavities. Anyway, okay, so things I'll send out today is the online lab. And like I stated, I will be there on campus. You don't have to, you can do it either on campus with me or at home. It will be due that day. Okay, so make some time uh, for that. And normally the time will be comparable to your regular labs. And then I'll have my Zoom open in case there's any questions. Okay. All right. Any questions? And then, of course, we'll leave the exam, which is due today, covering chapters 4 through 6. And if you have any questions throughout the day, feel free to shoot me an email. I'll be here. I got a ton of grading to do, so I'll be here after classes, way into the evening and grading. So I'll make sure I get your email answered as quick as possible. Okay. Any questions? All right then. Well, let me start with if you think of any questions concerning 4, 5, and 6 while we're talking, feel free to stop me and we'll definitely cover it. Okay. All right. Now, this chapter deals with chemical bonding. Okay. And you would think with all the chemicals out there in the world that there'd be a multiple different types of chemical bonding. But in actuality, there's only 2 types of chemical bonding. We're going to talk about those and determine how to distinguish the two. 2 totally different types of chemical bonding, 2 totally different types of properties due to the chemical bonding. Okay, but a lot of that down the road here, because this chapter is a little bit long, about 45 slides, actually about 40, take off about 2 slides. So first thing is this, is if you've not done so, the shapes table, we are going to utilize that shapes table quite extensively for this chapter. And that shapes table is, just to remind you, about a number of information on the top of it, but on the bottom there is a table called Table of Molecular Shapes and Bond Angles. Okay. Now here, this table, there's 2 columns. The first column is the generic formula, which consists of the letters A, B, and E. Now these are generic formulas that we're going to create based on the compound that we had to work, okay? And much more detail about what the letters stand for, but the letters, 3 letters, A, B, and C. And some, they do also have, may or may not have a subscript on B and E. But from that information, depending on your compound that you generate, which, by the way, the compound that we create comes from the valence electrons that the atoms associated with a compound bring to the overall compound. So for example, carbon dioxide, CO2, there's 1 carbon, there's 2 oxygens. So we determine the number of valence electrons for carbon, which is 4, okay? And then we know the valence electrons for oxygen, which is 6 apiece, and there's 2 of them. So that's a total of 12 valence electrons for both oxygens. And then the 4 from carbon, so 12 and 4, we got a total of 16 valence electrons that we have to work. From that information, we're going to be able to come up with a structure, okay? And from that structure that we come up with, we assign it a generic formula of A, B, or NE, if all those components are there. And using that information, we go to the table. And if we come up, for example, with AB4, well, AB4 is the most common geometric shape of chemical compounds. You can see in the second column, here's like a 3-dimensional picture of that geometry with the center atom, and then four moieties bonded to the center atom. and it has a specific name called tetrahedral. And there's a bond angle between those items, the elements that are bonded to the central atom. And that bond angle is 109.5. Okay, so here's the central atom in red, and then the other species. In yellow are the four moieties that are bonded to the central atom. Okay, and it's a three-dimensional model. It's an attempt to do that in the two-dimensional world that we look at. But its name is tetrahedral, and its bond angle is 104, and this is what this bond angle is, the most common bond angle. And then from there, like I said, this is the most common geometry of compounds. It varies, and we're going to use the information, and it'll tell us a lot once we get the general formula as to the structure. These here represent lone pairs of electrons on the central atom, which have a great effect on the geometry. Okay, you would think there's four moieties bonded around the central atom, as in the case we just did, but because of this lone pair, they're not bonded to anything. They tend to take up a lot of space, and they spread because they repel. Two negative charges repel, causing this bond angle here to be much less than 109.5. Okay, so lone pairs on the central atom have a big effect on the geometry of compounds, which then in effect have in turn have an effect on the properties of the compound. Okay, so we're gonna get to that point where we're going to come up with a structure. Let's go back. So if you're not printed the shapes table, yeah, do so we can make reference to it quite a bit. All right, so chemical bonding. As we talked about in the last chapter, the electron configurations that we worked with, the driving force of the atoms and any type of bonding is to obtain that noble gas configuration, where we have 8 valence electrons on the outermost shell, the outermost energy level of that atom. Okay, that's the driving force. So therefore, as we talked about, metals lose electrons, and in doing so, they become isoelectronic with the noble gas behind it. And so, for example, sodium, if you have your periodic table in front of you, sodium, in losing that one electron, now becomes isoelectronic with neon. That's the noble gas behind it. Whereas chlorine, by gaining an electron, becomes isoelectronic with argon. And in both cases now, the outermost shell is full with 8 electrons, okay? Because that's called the octet rule, except for hydrogen. Hydrogen does not have the octet rule, okay, because it has a duet rule. So its goal is to obtain 2 electrons around it so it becomes more stable. Okay. All right, so as we spoke about, just a rehash here, that all metals, okay, all metals lose electrons, and in doing so, they become cations or positive charge ions. Now, the magnitude of the charge depends on how many electrons they lose. Okay, so everybody in group 1A will lose 1 valence electron, so resulting in a +1 charge. 2A will lose 2 valence electrons and become a +2 charge ion, and the metals in 3A will become a +3 charge. Okay, so we refresh your memory on that. We need to become familiar as to the charge of the ions from the respective elements. Okay, and that is determined again by their position on the periodic table, and what group number they are in. The nonmetals, as we stated before, gain electrons. Those are the rules etched in stone. Metals lose electrons, nonmetals gain electrons. Okay, and in doing so, as I stated earlier, they become isoelectronic with a noble gas in front of it, and they become negative charge by gaining electrons, also named anions. Now, they also have the magnitude of the negative charge, again, depends on the group that they're in. And so everybody in group 5A, to obtain that H, requires 3 electrons. Okay, because they have 5 on the valence shell, they just need 3 more, resulting in a -3 for group 5A, -2 for group 6A, and -1 for group 7. Okay, so we got to be familiar with all of these charges. Now, when you have a metal nonmetal combination, we have the key aspect. A metal nonmetal combination, we have what's called an ionic bond. Okay, also an ionic compound. Okay, that's the definition of an ionic compound. Now, with respect to ionic bonds slash ionic compounds, is that they are the result of the elements, the elements losing or gaining electrons, resulting in a full positive or full negative charge. And when they come together, think of them as 2 magnets coming together and attract to each other and attach to each other. We tend to call it an ionic bond, but in true sense of the word bond, it's not a true bond, but we call it a bond anyway, because we're going to learn the next type. There's actual sharing of electrons. Now, with respect to ionic compounds, they are attracted to each other. Specifically, they are attracted to each other by an electrostatic attraction. Okay, basically like 2 magnets coming together and being attracted to each other and attaching to each other. Now, one component, one aspect or property of ionic compounds is as follows. Being ionic, the majority of them, literally all of them, exhibit solubility in water. Some ionic compounds exhibit total solubility in water and dissolve 100%, whereas some other ionic compounds maybe 5-10%, not as much, but nevertheless, there's still some of it that goes into solution. Okay, so the property I was speaking about is when these ionic compounds are placed in water, the electrostatic attraction is broken apart and they dissociate completely apart, either completely or a much smaller amount. Okay, now we're going to learn much more about that property. On your periodic table, there's a table called solubility rules. And we're going to learn the solubility rules to determine which ionic compounds are classified as soluble and which are classified as insoluble. But even if they're classified as insoluble, all that means is it's not 100% dissolved. Maybe 5% of it goes into solution. The point is this, is going in solution, the water, 100% water, does not conduct electricity. If you have pure water and you put some electrical probes on them, there will be no electricity being conducted because they lack ions to close the circuit. Okay, and so ionic compounds, when placed in a clean, pure 100% water, will then conduct electricity. All right. Some of them will conduct very strongly because they dissociate 100%, and some of them will conduct not so strongly because they don't dissociate 100%. So that's one of the properties of ionic compounds. So things like sodium chloride, you have a metal and a nonmetal. Okay, that is an example of an ionic compound. Now, when we start putting compounds together or ions together to make compounds, the thing to remember is this: you won't find two positives coming together to make a compound, nor would you find two negatives coming together to make a compound. That's because like charges do not attract. So two positives will repel. So in this case, the calcium ion and the lithium ion, both being positive, would not come together to make a compound. But they can combine with the bromide, okay? So the calcium can combine with the bromide to make calcium bromide, or the lithium can combine with the bromide to make lithium bromide. So it's a matter of the positive and the negative, and the anions and the cations coming together. And the other point about that is this: when you have anions and cations coming together to make a compound, you have to have enough of each so that their overall charges are canceled out. What do I mean by that is as follows. And this is the beginnings of actually making compounds. Now, if we look at lithium ion, which are positive charge, and then the bromide ion with a negative charge, well, they have equal charges. So I can put them together as a 1-to-1 ratio, okay? And when I put them together to write the formula, it'd be LiBr, lithium bromide, okay? Lithium bromide. Now, on the other end, if we have calcium ion with a +2 and we still got the bromide ion with a -1, well, I can't do the same with it. It's not a simple 1-to-1 relationship because I got a +2 from the calcium and a -1 from the bromide. So that tells me that I need 2 bromides for every calcium ion. Okay, so that 2 becomes the subscript for the bromide. So the formula would be CaBr subscript 2 for calcium bromide and for lithium bromide. And that's why when we look at ionic compounds, you see the subscripts, because you have to put them together with such a number of each, anion and cation, so that when they're together, they have a net zero charge. Okay, so that's one aspect to remember. Two aspects. One, they come together with enough charges to cancel each other out, and only positive and negatives come together to make compounds. Okay, there's some examples there of ionic compounds. So that's, if you look at a formula, you're given a formula, and they're asking you, is this an ionic compound or the other we're going to talk about? Well, simplest thing to do is to look at them, look at the two atoms, and determine if they're a metal and a non-metal. Okay, and if you forget about if an element is a metal or not, remember, use the periodic table in that stair step. To the left of the stair step are all the metals except hydrogen. Remember that hydrogen, though it's to the left of the stair step, is not a metal. It's over there on the left side because it has one valence electron like everyone else in group 1A. And everybody to the right of the stair step of the periodic table are nonmetals. Okay, so it's not necessary to memorize the property of every single element there. Let me clear this up a little bit. Now, when we get a combination of nonmetals, remember, a compound is 2 or more different elements. So when both of those are nonmetals, we have covalent compounds. They have covalent bonds. What that means is now with ionic, unlike ionic bonds, where you have a full charge and a full negative, here you don't. You have a sharing of electrons between two atoms. Okay. For example, if I were to write the structure for hydrogen gas, I have hydrogen, And then I would write a line to represent a bond between the two hydrogens. That line represents two electrons, okay? Every bond will have two electrons. And we're going to have double bonds, which has a total of 4 electrons, and triple bonds, which has a total of 6 electrons, okay? So a single bond has 2 electrons, which there are being shared between the two hydrogens. So if you think about it, now look at the hydrogen. Hydrogen has 1 electron, right? And another molecule, another atom of hydrogen has 1 electron. Notice these can combine with each other, okay, and share those 2 electrons with each other to have more of a stable state, because that single electron all by itself is not very stable, and that's why a lot of the diatomic elements combine with other elements of themselves so they can have a stable configuration, a stable bond. Okay, now in this scenario, we have within the covalent compounds, there's a subset. Okay, the subsets are both covalent, but there's a difference in how the electrons are being shared. In this scenario, when the two elements are the same, the sharing is equal. Think of it as a tug of war with 2 people with the same weight, same strength. That tug of war or that rope is not going to move. It's going to stay stable. We're going to be an equal state. So here we have equal sharing. Okay, but it's also possible to have a covalent bond with unequal sharing. And that happens when one of the elements in that bond, in that covalent bond, are different. That's simple. Notice 2 hydrogens are together. A hydrogen and a chloride, not the same. Okay. Now, the last chapter, we had talked about the property of electronegativity. Remember that? En? And electronegativity was a measure of the affinity of electrons. Let me restate that. Electronegativity is a measure of the ability of an atom to attract electrons onto itself when it's bonded with another element. And we looked at the periodic table, and I stated, okay, fluorine in the top right corner of the periodic table is the most electronegative element there is, plain and simple. And so if whomever fluoride was bonded to in a covalent bond, it is going to pull the electrons more onto itself than the other elements. So it's because they're more electronegative. Unless it's bonded with another fluorine, then you have equal pulling again, okay? So in this scenario, what we did is we used fluorine when we talk about En as our benchmark to determine whether how electronegative, because every element has their electronegative value, and it's not necessary to memorize everybody's value. All you got to do is remember that fluorine is the most electronegative element, and the trend went from left to right, it increased, the En, and from the bottom up, it increased, all pointing to fluorine. So to determine who's the more electronegative in the bond, in this example, we have hydrogen, which is in the far right of the table, and then chlorine is right below fluorine. So their position, hydrogen and chlorine, relative to fluoride, you can see from the periodic table that chlorine is a lot more electronegative. Therefore, in this example we just talked about here, the bonding, the electrons are being pulled toward the toward the chloride more so than toward the hydrogen. Okay? The result is this. it creates what we call a dipole. Now think about the dipoles that are around your life. In fact, we live on the dipole. Isn't that the Earth? Because we have two poles, the North Pole and the South Pole. That's dipole. All right. And a battery is a dipole because they have a positive charge and a negative charge. Well, because the chloride is a lot more electronegative than the hydrogen, it pulls the electron density, more electron density of the bond onto itself. The result is the following. It creates the lowercase delta by partial, what we call a partial negative. Okay, partial negative on the chloride. I like this what I'm talking about is going to come up over and over again. We really have to grasp it. On the hydrogen, it has a partial positive. Not like a positive charge on the ionic compounds where they have a full charge, a full positive, a full negative. With covalent compounds, what is created is a partial charge. Okay? Notice when it's equal sharing, there is equal pulling. There's not one area has more electron density than the other. It's all equal. Unlike unequal sharing, where because of the electronegativity of chloride being greater, is pulling the electrons onto itself much more so than the hydrogen is, resulting that the more negative character on the chloride and more positive character on the hydrogen, okay, resulting in a dipole, which then helps us to determine some physical properties of these two compounds, because we use as reference points oil and water. Oil is a very, what we call a non-polar solvent. Oil. Non-polar. And water is considered a very polar solvent. Okay. So let's think about this, for example, for a minute. We know that oil and water do not mix. Try putting a little bit of vegetable oil and a glass of water and some water together and see what you get. You get two distinct layers. They totally do not mix. Okay? Because of the physical properties of the oil and the water. The oil is nonpolar, the water is polar. Once we determine that a species has a dipole, like this example here of HCl, it results in a polar bond. Okay? Polar because we have a partial positive side and a partial negative. When there's equal sharing, we have a non-polar bond. Okay? Which then, having all nonpolar bonds tells us that the overall characteristic of that molecule means that it is a nonpolar species. Therefore, if I were to see if it was soluble in oil or water, knowing that it has a nonpolar bond tells me there would be more soluble in oil than it would in water because of differences in polarity. Whereas HCl, being polar, would dissolve much more readily in water than it would in oil. Okay? All again due to the polarity, which is due to the equal sharing or the unequal sharing of the bond. Now we're going to elaborate on this aspect on this much more down the road, because you will see that occasionally when we deal with a polar bond, that depending on the structure, if the polar bonds do not cancel each other out, then we have an overall polar molecule. But if the polar bonds do cancel each other out, then we end up resulting in a non-polar species. Okay? And much more on that down the road here. So we have here a combination of a metal and non-metal, and we have covalent bonds, covalent compounds, where we have sharing of electrons. Okay, sharing of electrons. So some examples of covalent bonds are obviously all the diatomics, covalent bond, okay? And, water, H2O, because you see hydrogen and oxygen, both nonmetals. Next example, there's CO2, carbon dioxide, okay? Both of them are nonmetals, so we have covalent compounds. Now, earlier I said with the ionic compounds, one property about ionic compounds is when they dissociate, when you put them in water, they dissociate either fully or partially, but they dissociate nevertheless. Covalent compounds do not do that, okay? Once you put them in water, they stay intact structurally. Okay, so carbon dioxide, for example, I'm sure we all drink carbonated drinks. That's nothing more than carbon dioxide in water. It does not break up into the carbon and the oxygen atoms. It maintains as carbon dioxide. Okay, and earlier I stated if I took the ionic compounds and I put it into pure water, I end up with a conducting solution because of the ions. Well, covalent compounds, because they do not dissociate into ions, the result is you have non-conducting property. There is only one example of a covalent compound that will dissociate, but that deals with the chapter we're going to have down the road, acids and bases, but it's the only example. In fact, you have one in your stomach right now, hydrochloric acid. That's a covalent compound, but it does dissociate. That's the only example that does. The covalent compounds that dissociate, those are acids that release a hydrogen, what we call proton, which is contributes to the acidity of whatever you're working with. Okay, much more on that down the road. All right, so they do not dissociate. Now, we're going to start with ionic compounds, and we're going to start putting together, learning to put together structures and elements, ions specifically. And so, here's the thing, is you could be given the formula, for example, and being asked to give the name, or you could be given the name, written out the name, and asked to write the formula. Well, in doing so, when you're given the name of the formula, and it's an ionic compound, you have to know the ions that are generated first before you can put them together correctly. Okay. For example, let's do an example of what I just stated. Okay, so it could be write the formula for aluminum chloride. Okay. All right, so you're asked to write the formula for aluminum chloride. Well, before we can do anything, we have to write, first notice that we have a metal and a non-metal combination. So that tells me that I'm dealing with an ionic compound. Okay? All right. And notice the name, aluminum chloride. There are no prefixes here. More on that in a second here. So first things first, we look up aluminum on the periodic table because we don't know the charge. Let's say you don't know what the charge is on the ion. And so you look it up and you can see that it's in the group 3A metal, meaning 3 valence electrons, which is going to lose 3 electrons because it's a metal. So its charge will be +3. Okay. Chloride. Okay, notice it didn't say chlorine. Chloride tells you you're dealing with the ion. It belongs in group 7, originally chlorine, and when it becomes chloride, it picked up 1 electron. So it ends up with a -1 charge for the chloride ion. Okay, now I want to put these together to write the formula. Well, notice, as I stated earlier, I got to put enough of each so they cancel each other out with respect to the charge. Now I got a +3 on the aluminum, only a -1 on the chloride. So that tells me that I need 3 chlorides to cancel out the +3 of aluminum. So that 3 becomes the subscript. So aluminum, Cl subscript 3. Okay. And that is the formula AlCl3 for aluminum chloride. And notice that there, I didn't say aluminum trichloride. Okay. Just a straightforward aluminum chloride. If we were to do barium chloride, it would be BlCl2. We can run through that exercise and you see that's the formula. Notice I call this barium chloride, not barium dichloride. Unlike ionic covalent compounds, that the name of this, you recall the name of CO2? Carbon dioxide. And then another one, another example of that one with only one oxygen, carbon monoxide. Okay. Note that when we're dealing with covalent compounds, and this is a precursor to what we're going to talk about here in a bit. When we start naming them, covalent compounds use prefixes, mono, di, tri, tetra, etc. With ionic compounds, no prefixes. So aluminum chloride is straightforward. Aluminum chloride, not aluminum trichloride. Okay. Unfortunately, if you look at the packaging, I think marketing, because back earlier, there used to be times that a lot of the chemicals were given names like that, like aluminum trichloride. And there was a lot of ambiguity going on in the world of chemistry. So there is an organization, worldwide organization, whose responsibility is to come to a common name that the world accepts for compounds. And this is one that they got rid of this trichloride and so forth because it became somewhat ambiguous. We'll learn more about that in a bit. Okay, so no prefixes for all ionic compounds when you start to name them. Which, by the way, don't forget your nomenclature exam. You have unlimited attempts. All right. Okay, so the question here was wine. Wine, the form is CaBr2. Okay. And simply because the ion of calcium is a +2 and the ion of bromides is a -1, and therefore we need 2 bromides for every calcium ion. Okay, so that's why the formula becomes CaBr2. Now keep this in mind too when you see that formula. Okay, sometimes I've seen that for whatever reason, with respect to the bromide, okay, notice this is Br2 by itself is simply bromine. Okay, diatomic bromine. Okay, and sometimes for that reason, people, not all people, not all students, but they would treat this and say calcium bromine, thinking that this is diatomic bromine, but the thing to remember, that is incorrect, okay? So you'll always find with respect to writing the formula for ionic compounds, you will find a metal written first, followed by whatever is bonded to it. In this case, we have bromine, and because there's a +2 on the calcium ion, we need 2 bromides, okay? So this is calcium bromide, So seeing a metal first tells you that if there's bromine or Cl or I for hydrogen, it's the ide. It is the ion, not the bromine. Okay, not diatomic bromine. All right. All right. The question here is, which compounds are ionic? So by definition, what is an ionic compound? How do we define an ionic compound? Remember?
Isn't it when like two bonds that are equal are connected? Is that what that is?
Not quite. Remember, there's two types of bonds, two types of compounds, ionic compounds and covalent. Okay? And so here the question is, which compounds are ionic? So we have two types of compounds / bonds. Okay? The one is ionic, and the other type is called covalent. Now remember how we distinguish, how do we determine by definition what constitutes an ionic bond / compound? Which two types of elements have to come together? Remember? Metal / non-metal. Okay. Covalent compounds is a combination of non-metal and a non-metal. Okay. So those are the two definitions of an ionic compound and a covalent, and that's how we determine whether one is if we're looking at bonds, whether it's ionic bond or a covalent bond. Okay, so let's look at the first one, potassium bromide. Do you think that is an ionic or a covalent compound?
Ionic.
Exactly. So that's ionic, and that's because we have potassium and a bromide combination. Okay, now granted, a lot of these you may not know what they are, but that's okay. But you know the elements. So what about the second one, SO3?
Covalent.
Yeah, it's correct. That'll be a covalent. And hydrochloric acid, HCl.
Ionic.
Ionic.
Oh,
Hydrogen is a metal or non-metal?
oh, it's a non-metal.
Yeah, and chloride we know is a non-metal, so we have a covalent. Okay, and then how about Br2? Ionic or covalent?
Covalent.
Covalent, exactly. We've got two bromines together. They're both non-metals. It's
What if
covalent.
there's two metals together?
Well, you won't find two metals together, at least in Chem 130. So in other words, and remember we talked about if we have this hypothetical A plus and a hypothetical B plus, and they're both metals, well, they would not combine. Okay, why wouldn't they not combine?
Because the two positives repel.
You got it. And even if we had a negative A and a negative B, those two would not combine. Okay, because again, the negative and the positive charges repel. So you won't have that combination nor that combination. Okay. And yes, there are examples of compounds beyond the scope of Chem 130. We have multiple metals or are involved, but for our sake at Chem 130 level, it's always going to be a non-metal, metal, and metal, non-metal combination. Okay. So what about CO2? What do you guys think that is? Is that ionic or covalent?
Covalent,
Exactly. And then the last one,
ionic.
ionic. So of all these, only two of them are considered ionic. The question could have been which compounds are covalent, okay? But they're asking which is ionic. And granted, you may not know what these guys are, SO3, but this one is called sulfur trioxide. It's a waste gas that gets into the environment and goes up to the clouds and reacts with water, and then eventually forms sulfuric acid, and which is acidic, and then drops back down when it rains into the soil and causes problems. But occasionally, and if you're ever behind a car and you got this rotten egg smell coming out from the car, it's probably some of that coming out. It's one of the exhausts of our fuel. This is what's in our stomach, HCl, hydrochloric acid. Now, here's the thing about HCl when we name it. When we name HCl, and then if we have HCl aqueous in water, when it's just, let's say, hydrogen HCl gas, it is called hydrogen chloride, okay? But when it's in a solution, it's called hydrochloric acid, okay? And so some of the questions in the nomenclature exam, they use HCl, HBr, any of the acids like this. And if you write, I go back and give everyone credit. If you write hydrochloric acid, Canvas treats it as incorrect, which is not 100% correct. But anyway, I just want you to be aware of the differences in naming, even though they are the same compound, where they are physically in the gas phase or in the aqueous solution, they are given different names. Okay. And then we got bromine and then carbon dioxide. That HCl, by the way, is what's in your stomach. So you're walking around with hydrochloric acid. Okay, so those are the two ionic compounds. In naming this, KBr would be potassium bromide. What about if I had to name the MgCl2? What would its name be? This one right here. What would its name be?
Magnesium chloride.
You got it. Okay. Not dichloride, because remember, ionic compounds, no prefixes. So we got potassium bromide, magnesium chloride, and yeah, there we go. So you'll see as we proceed with making compounds, I'm going to throw in, name that compound. All right, now with respect to ionic bonding or ionic compounds, notice here we have the sodium atom. Remember, when we look at the electron configuration, for sodium, here, let me just get this right. Okay, here we have the sodium atom right here. And the electron configuration is 1s, 2, 2s2, 2p6, and then it's in the third energy level, so it's 3s1. So its valence shell is in the third energy level. It's got one valence electron, okay, which is consistent with this sodium being in group 1a. Well, being a metal is going to lose that one electron, okay? So now it has a +1 charge. So the electron configuration now for the ion is as follows. The new valence shell is now in the second energy level. And so it has shrunk. The radius has shrunk. You can denote it here by the shape of going from the atom to the ion. Okay. Now, with respect to the chloride atom has room for one electron because the chloride is, you've got three, it's got the 3p5 electron, 3s2. I'm looking at the valence shell right now. I'm not going to give the whole electron configuration. So the chlorine atom has room for one electron, okay? And when that happens, it becomes 3s2, 3p6. Now there's 8 electrons around it. So it goes from the atom to the ion. And in picking up electron, that one electron takes up more space. So what happens, the ion of the anion, the chloride, is bigger than the atom itself. In converse to the metal, in losing an electron, the atom radius is much bigger than the ion, the resulting ion, because it lost electrons. Okay? And the fascinating thing about this this example here, though it's not balanced, the fact is that there's just a transfer from here to here of one tiny little electron. The electron that sodium gave up is picked up by the chloride atom. And sodium metal by itself is very, very hazardous metal. Sodium metal, if I put it in some water, it would react violently, give off a lot of heat, give off hydrogen gas, and the heat that it generates will actually ignite the hydrogen gas and it will explode. Chlorine, which normally consists of the diatomic chlorine, is a poisonous gas. Okay, so we have a poisonous gas, a hazardous metal. One electron, one tiny electron, keep in mind, that electron literally has a mass of 0. We assign it in a relative mass of 0, so tiny compared to the proton and the neutron. And in having such a low mass too, it has properties of light. It travels like light and has specific energy levels with respect to the electrons of atoms. And the transfer of one electron results in a species that we can put on our French fries, not too much, have too much of a problem. It's not as hazardous unless, you got blood pressure to deal with, and that sodium ions can play havoc on that, okay? One tiny electron. To me, that's mind-boggling as how the effects of one tiny, tiny chunk of matter could change the properties, totally change the properties. Anyway, little side note there. Okay. This basically notice the change in the size of the radius from atom to ion. All right, so let's consider the magnesium and the sodium atoms from the elements, okay? And then we're going to also take their respective ions. And we're going to look at the number of protons and electrons for each, and then why the ions bond together, okay? Well, we know that the magnesium atom has 12 protons and 12 electrons, okay? It's element number 12. It's a metal, it's in group 2A, so it will lose those 2 valence electrons, and resulting in now having 12 protons, but now instead of 12 has 10 electrons. It lost 2 of them. So the net charge is a +2. 12 positives, 10 negatives, net +2. The sulfur, being in group 6A, has 16 protons, 16 electrons. It's a nonmetal, so it would gain electrons. Okay, it's striving to get to the octet, and in doing so, the ion now has a -2 charge because it needed 2 electrons to get to that magical 8 number. So now it has 16 protons and 18 electrons. Okay, so the net mathematically is 16 positives, 18 electrons. Net is a -1. Okay. Now these two can come together to form a compound. Why? Because they are oppositely charged. Okay, they're not the same charge. And so I can put the respective ions together to create MgS as the formula. Okay. If I had to name that, what would be the name of the formula we just created? Anybody want to give a shot at it? MgS, what would be its name? Anybody want to take a shot? What about the Mg? Name that. Magnesium. Okay, what about the S? Is it sulfur or sulfide? It's sulfur when it's the atom. When it gains an electron, it becomes sulfide. So the name here would be magnesium sulfide. Now, given the metals that we've been working with, you can interchange. We dealt with all of them. Sodiums, you can make sodium sulfide, potassium sulfide, cesium sulfide. The group 2 metals, you got beryllium sulfide, calcium sulfide, strontium sulfide, barium sulfide. So you start building up a database of all these compounds that you can start putting together just by playing with the cation and the anion, and then remembering to put enough together to cancel their respective charges out. Okay, so let's kind of recap a little bit about the ionic charge. Cations have lost electrons, so there are more protons. So what is happening, a couple of things are happening. One, it lost electrons, so the outermost shell disappears. Okay. Furthermore, it still maintained the positive protons, nothing changed there, but it has less electrons. So there's more positive nuclear force on the remaining electrons. The result is they do a much stronger pull on the remaining electrons that are left and resulting in a smaller atom. Not only by that, but coupled by the fact that they lost that valence shell, okay, by losing those electrons. Whereas the anions gaining electrons, there are more electrons now in the valence shell, and therefore they start to repel each other, obviously, because negatives will repel, just like positives will repel, and the orbits are pushed away, resulting in a larger radius than the atom. Okay, so you may have questions like this: true or false? This is regarding an ionic bond between aluminum and iodine. Okay. All right. So it says here the aluminum atom loses electrons and the iodine atom gains electrons. Okay. Also keep in mind when you read these questions that in order to be a true statement, all aspects of that question must be true. Because you may occasionally get a question and only one part of that question is true, is false, and then the whole thing will be false. Okay, so what do you think here? The aluminum atom loses electrons. Is that a true statement? No? Anybody there?
Is that false?
Okay. Aluminum atoms lose electrons. Okay. Is aluminum a metal or non-metal?
Metal.
Okay. And what happens to all metals?
They they gain, right?
No. All metals lose electrons. Okay. And if metals lose electrons, what must be true for non-metals?
They gain.
Exactly. Okay. So first part, aluminum atom losing electrons. To answer that, we have to make sure that we're dealing with a metal, which of course aluminum is a metal. So that part is correct. True. But let's check the second part. Iodine atom gains electrons. Is that a true statement?
Yes.
Yes. So the overall question is true. Okay. Overall question is true. Yeah, questions that sometimes they could have been written like the iodine atom loses electrons. What can happen? There's a lot of questions when you are, or let's say you're applying to graduate school and there's like I forget the name of the exam to get into graduate school, and a lot of exams. There's questions like that that kind of trick you, and questions like I recall questions like if you're on the line waiting to get a ticket and there's a lady with a blue hat in front of you and there's two ladies down, she's another lady with a yellow hat. What time is it in China? And I'm like, what? Crazy questions, but the type is where the bottom line is this: just you got to read the question carefully and look at the question. And in order, if they're telling you true and false here, then that whole part of this question has to be true in order for this to be true as an answer. If any part of it is false, then it's a false statement overall. Okay, how about this one? The aluminum atom is larger in radius than the aluminum ion. Okay, what do you guys think? So the aluminum atom, okay, which will lose electrons because it's a metal. So who's bigger, the atom or the ion?
The atom.
The atom, you are correct. Okay. So that would be a true statement because the atom lost electrons, aluminum lost electrons. So now the next shell is next one in. Plus, there's more positive charges, more protons, nuclear charge on the remaining electrons that are there. So they pull them in even closer. Okay. All right. Now, the converse, the iodine atom is smaller in radius than the iodide ion. Okay. And to answer this, think about it. It is the non-metal, so it's going to gain electrons. So we can expect that the ion will be larger because you got one more electron or more 3 to 1 more electrons in the outermost shell. Okay, resulting in more repulsion of the other electrons, resulting in a bigger radius for the ion. Okay, and then here the aluminum and iodide ions form a bond by attraction. What do you guys think? Is that a true statement?
Yes.
Yes, okay, because we're dealing with an ionic compound, ionic bond. We got metal, non-metal, full positive charge, full negative charge. They come together like the magnets do that I have here in my hand. Okay, no sharing of electrons here. All right. Not much to say about metallic bonding, just to say that the metals themselves are just loaded with electrons, and that's why they're a good source or a good material to create, electrical wiring and so forth. Also, the only aspect to say is because they're good conductors of electricity. In fact, anything that is a good conductor of metals, that is a good conductor of electricity, also conducts heat. It's a good conductor of heat. Anything that does not conduct electricity, they're good insulators, actually. The opposite. All right. Which brings us to, we talked about ionic bonds. Just to rehash, ionic bonds is a metal, non-metal combination, full positive, full negative charge. They come together by electrostatic charge. If I put them in water, they will dissociate, okay, and break apart. Now, with covalent bonds, there's an actual coming together of electrons and sharing, okay? And so with respect to ionic bonds represented by my hands come together, there's no sharing of electrons. They're just coming together here. With covalent bonds, look at my fingers intertwining here. All right. My fingers represent electrons that are shared between two atoms. And there is a sharing of electrons. All right, so and we're going to have three types of bonds. We're going to have a single bond, a double bond, and triple bonds. And what normally happens is we tend to draw a line to represent a single bond, okay, which you can also draw by writing or two dots. Okay. Excuse me. But when you're writing structures, it's just much easier to just draw a line. Okay. Now I'm going to draw, A and B, two atoms that are bonded to each other, and I draw a line to represent that bond. You can also draw two dots. Now with double bonds, we draw two lines, okay? And that represents a double bond. Now keep in mind, when we draw that line, those two electrons, there are two electrons in that line. Those two electrons are being shared by both A and B, okay? Which is going to be unequal sharing or equal sharing, but for right now, we're just sharing, okay? Just sharing it. So I can count those two electrons to count toward A, toward the octet rule, and I can also count those two electrons toward B when we're counting for the octet rule, okay? Remember that, keep that in mind. Now over here, every line represents two bonds, so we have a total of 4 electrons for a double bond. And I can write them with lines, but some people also do the dots, and that's fine. Each dot represents an electron, okay? And again, these 4 electrons are being shared by both A and B. And then finally, we have 3 lines, which represent 6 electrons, okay? And again, you can draw them with the lines or draw them with the 6 dots. You can see it's a lot of dots right after a period of time. So, and these 6 electrons, again, are being shared toward the A and B, okay? So, for example, okay, because we're going to use this a lot when we're looking for the octet. Let's take this example here, and we're going to put 2 electrons there and 2 there. Okay, now if we look at it simply at A by itself, okay, A has 2 electrons on A itself, just by itself, but 6 of them are being shared with B. And then we got the 2 here all by itself. So total, we have 8 electrons around A. 6 of them are shared and 2 of them are not shared. Okay, they're on the atom itself. The same is true for B. There's 6 of them being shared and total of 8 here. And then there's 2 of them not being shared. And so B also has 8 electrons. So in this scenario, A and B have fulfilled the octet. Okay. We're going to be doing a lot of that. But think to remember, whenever there's a bond, those electrons in the bond are being shared by 2 atoms. So they count to each atom individually. Okay. All right. So we have single, double bonds, single, double, and triple bonds. Let me clear this up here. There are space field models, and that's what these models are here. They kind of represent the electron density around there. We also have, we use space field models, we use stick models. Most of the time it's stick models, but space field models, this represents carbon, the dark color, and then we got oxygen on both sides, okay, in red. So this is a model of carbon dioxide, and then over here we have a model of space field model of H2O water. The oxygen is in red, the hydrogens are in white, okay? But they are, this is an example of covalent bonds, bonding or covalent compounds. 2 nonmetals, minimum. This is a rehash of what I just talked about, single bonds, 2 electrons, double 4 electrons, triple bonds, 6 electrons. So that's the max you're going to find. You won't find more than, for Chem 130, you will not find more than 4 bonds around an element, okay? For example, and I'm going to give you generic examples here. You have, let's say, A bonded to B 4 times, 4 bonds. Each line represents a bond to B. So you can see there's 8 electrons around A, okay, 4 bonds. If we take A and triple bond it with B, and then maybe hook it up again with another B, notice that A, we're looking at A right now, we don't have to worry about B, but A has 4 bonds around it. 1 single bond and 1 triple bond, a total of 4 bonds, okay? A total of 8 electrons. Here in this example, we still have 8 electrons, but there are 4 single bonds, okay? But the octet has been fulfilled in both examples here. Okay, now with respect to single bonds are the longest in radius when compared to the bond length between 2 atoms, and generally the weakest, whereas triple bonds tend to be the strongest and the shortest, and they're also packed with a lot of energy, So now, when it came to covalent compounds, in the case of ionic compounds, when the atoms came together, the bond length, the radius between the nucleus of each one was fairly straightforward, okay? Meaning that when we had one ion coming together with another one for an ionic compound, okay, the radius there, this is the radius between the two, this is for ionic, because simply the sum of the radius of each individual element, okay? Because there's electrostatic attraction, they're just like 2 magnets coming together. And the radius, total bond length is a simple, straightforward sum of the radius of each. So it was thought that for covalent compounds, the same would be true. So if we look at the hydrogen atom, which is known to have a radius of 0.037 nanometers, very small diameter. Nanometers, that's in the order of 10 to the negative 9 meters. And the chloride atom, okay, has a radius of 0.099 nanometers. It was thought that it would be very similar to this, that the overall radius would have been the sum of each individual radius. So the sum would have been 0.136 nanometers, okay? But that's not the case. It turns out that radius in that bond length was actually much less than the sum of the individual atoms. And what is happening is that there is an overlap due to the sharing of these electrons between the hydrogen and the chloride. And we have an overlap, so the overall radius, bond length, is much smaller than the sum of each individual radius, like the ionic compounds. But for covalent compounds, because there's this overlap that I just explained with my fingers and demonstrated, because of that, okay, the bond length is much shorter. Okay. All right. Now, let's briefly talk about energy, and then we'll take a quick break. With respect to bond energy, thing to remember or keep in mind that energy is required to either when you break a bond. Let's say I got a bond here, it takes energy to break it apart. Bond. It also takes energy to put it together. Okay. And there's two kinds of energy that we talk about, which when we're breaking bonds always require energy. Think about it, it makes sense to, okay, I need energy to break that apart. Okay, I got a bond here. Okay, and that requires energy. And so what is happening is that energy is being absorbed into that reaction, and it is called an endothermic process. Okay. A classic example would be if you go to the pharmacy and buy a cold pack. Cold pack is a couple of chemicals in a container, plastic container that you take and you smash. You may or may not use one of these, but when you smash them, that pack gets cold. Okay, because in that chemical process is an endothermic process. It's taking energy from the environment and absorbed, and it actually gets cold. Okay, and we call that endothermic process. And being an endothermic process means that energy / heat, when we talk about heat, corresponds, it's just the same as saying energy, because you got to put energy and that creates heat. It is a reactant. It's on the reactant side of this chemical process. We're breaking up the bond of HCl. We got to put energy into the system to break it back into the individual atoms, separated. Okay. Now, when we're forming bonds, bringing elements together to form a bond, there's a release of energy. And we call that exothermic process. Again, back to the pharmacy, there's also cold packs that you can buy, smack them together, and they get hot. So you can put them on, sore muscle or sprained ankle, something like that. Okay. Those are hot packs. That is an exothermic. It gets warm when the process, whatever process is occurring in that plastic is giving off heat. So in this case, energy / heat is a product, and we write it in the product side right here. So it's a reactant, becomes endothermic. When it's a product, it's called exothermic. So this gets cold, and this releases, this gets hot, warm. And here we have an example of the hydrogen atom, so it's just the opposite we just showed you up here. of the hydrogen and the chloride atoms coming together to form a bond, HCl. All right. Okay, tell you what, I got 11 at 1:30. Let's come back at 1:45. Take a short break and then we will continue. So call it 1:45. Okay. All right, well, let us continue. Let's answer these questions here. The questions are true and false. And they're asking you about this compound, H2S. Now, obviously, I know you may not know what this is. That's okay. It's hydrogen sulfide. Very nasty smelling material. Anyway, here the question is, electrons are shared in H2S. Okay. How would you answer that? How do we know that electrons are shared in H2S? Any ideas? Well, to be shared, they have to be covalent compounds, right? And so the question is this a covalent compound, covalent bond? And that's between hydrogen and sulfur. And to be covalent, they must be two nonmetals. So is are hydrogen and sulfur nonmetals? And yes, they are. Therefore, yes, it's a true statement that the electrons in this particular compound are shared. And we answered that question by first defining if we got an ionic compound or a covalent compound. And to define that, we had to determine whether we're dealing with a metal-nonmetal combination or non-metal combination. And in this case, it's a non-metal combination, therefore they are shared. Down the road, we're going to ask questions like, look at what kind of sharing? Yes, they're shared, but is it an equal sharing or an unequal sharing? Okay. Now, the bond between HS, is it ionic? Well, we just answered the fact that it's covalent, so therefore this would have to be a false statement. No, they're not. They're not ionic, they're actually covalent. And then here, the bond length between the hydrogen sulfur bond is less than the sum of the two atomic radii. And that, again, would be a true statement because we went through that example of hydrogen chloride, where they created a bond, and it was anticipated that the bond would be the sum of the radii of each individual atom, but it wasn't. It was much less because of the overlap in that bond, in that covalent bond. Now, breaking the HF bond releases energy. What do you guys think? You want to break the HF bond. Is it going to release energy?
Yes.
Now, remember, and this could be confusing. Sometimes it's hard to remember which is which. But anytime you want to break something, it requires energy. Okay? And so here, the HF bond requires energy to break. It is when we form the bond, that energy is released exothermic. Breaking bond is endothermic, and forming bonds is exothermic. Okay, which brings us to Lewis dot structures. Okay, and specifically of atoms, but this is the precursor to looking at Lewis dot structures for molecules and compounds, which then, once we learn how to do that, we use the shapes table to figure out the geometry, okay? All right, so this, for the atoms itself, and this only pertains to the metals, 1A through 8A, okay? And it's simply writing in down the number of valence electrons around the symbol, okay? We identified the valence electrons, and then that's given by the group number, okay? And you simply put a dot around the atom for the number of valence electrons each atom has, okay? And you just go kind of pretend that the atom symbol is a square. And so you start off on one side of that square and put a dot, and you go around that all four squares and you put a dot at each side. And then if you're going to add more, now you double up and you continue to go around until you got them completely full with the 8, depending on the atom. So, for example, they wanted you to draw the Lewis dot structures for these atoms: potassium, oxygen, silicon, magnesium, and iodine. Okay, no problem. All you do is find them on the periodic table, what group number, determine how many valence electrons, and there you go. You got potassium, which is a group 1 dot. Where you put it on that symbol makes no difference. You can put it where it is there in potassium, or put it on top or the bottom or to the left, either way. Excuse me. Oxygen is in group 6, right? So we have 6 electrons, okay? Notice that those 2 electrons on top and the bottom are separate. So what we do is go around the horn, go 1, 2, 3, 4, 5, and 6. Let me draw that out to demonstrate that. Okay, we do that because that is consistent with the fact that how we feel the energy, the electrons in the electron configuration. So, you know, this is 1, 2, 3, 4, 5, and 6. Okay. And if this was, let's say, neon, then obviously neon has 8 electrons. So we can go 1, just go ahead and put those 8 all the way around. Okay, 8 electrons, 8 valence electrons. Okay. All right. And that's pretty straightforward as far as drawing the Lewis dot structures for the atoms. Just a matter of writing down how many valence electrons they have. Okay, now when we are talking about specifically Lewis dot structures, okay, we're going to tally up the total number of valence electrons that every element, every atom brings to the structure. Okay. Then you're always going to be told who the central atom is. Either the central atom will be in bold print, and or to be an underline, and then whatever follows, you know, element-wise, is what is bonded to the central atom. Okay. For example, what do I mean by that? This is CH4. This is methane, it's a hydrocarbon, but we could underline C here, and that tells you that carbon is the central atom. And so very quickly you can put carbon and draw 4 bonds, okay? Because there's 4 here, 4 hydrogens, and then attach 4 hydrogens around it. See how that goes? All right. Or one could say carbon, this example of carbon, H3Cl. Again, carbon is the central atom, and then there's 3 hydrogens and a chloride bonded around the central atom. So we got 3 hydrogens, and then we got a chloride around, see? All right. So That's what we mean by the central atom, and everything is bonded around the central atom. The only time you don't have a central atom is when you have two atoms. There's no central atom when you got, you got to have at least three atoms in your structure to have a central atom. If you only have two, then no one's really a central atom if you only have two species. All right. So once we do that, we have to remember the goal here is to make sure that with respect to valence electrons, that the octet rule is followed, except hydrogen. Hydrogen has two. So what that means is as follows, is that hydrogen will always have one bond. That's it, one bond. You will not find hydrogen bonded having two lines like this. You will never find that, or even three or even four. Always one bond, okay? So, but everybody else has to have 8 electrons around it. Now keep it in mind, this is covalent compounds. And those 8 electrons will be shared, can be shared, could be shared with another atom. And they count towards both the other atom and the one you're looking at, okay? There's also electrons that are not shared. They're not bonded, okay? We have electrons, for example, that we call bonding electrons and then lone pair. Let's do an example of that. Oxygen, for example, water, H2O. We're going to go through this here in earnest, this structure. We end up with this, and then we can draw a set of 2 lone pair or 4 dots, okay, of electrons. Now notice around oxygen itself, there's 8 electrons around oxygen. There's 4 of them, 4 electrons that are lone pair. They're not shared with anybody. They're on the central atom, okay? And then we have 4 electrons, 2 on each hydrogen, total 4 that are bonding, okay? And then we need to identify this because this goes back to the general formula of A, B, and E, okay? A always represents the central atom. You're always going to have one A. So the general formula for this structure we just put together will start with A, okay? B and X represents a number from 1 to 4, okay? B represents whatever is bonded to the central atom. So we can see they can be the same or different. We can see that, yes, we have B here. In fact, we have 2 Bs, 2 hydrogens are bonded to the central atom. So it's AB2, okay? Then the E are the lone pair on central atom. Okay, I repeat, keyword on the central atom only. We don't care about lone pairs on any place else, just what's on the central atom. And so, yes, we're going to have an E there. And that's, excuse me, we have 2 lone pairs. Sorry, all this dust of this wind floating around here is really playing havoc on my coffee and my asthma and stuff. It's crazy in my eyes. Anyway, so the general formula we have for water would be AB2E2. A is the oxygen, B, there's 2 hydrogens, okay, and in E, there are 2 lone pairs. See how that works? That means that from that information, we then go to the shapes table and we look for AB2E. There it is, the last entry. There's the three-dimensional picture of this, could, like I said, could be water, where you had the central atom of oxygen, and then those two are hydrogen bonded to it. And then there's two lone pairs of electrons. Well, the geometry of that configuration is called bent. And that bond angle is much less than 109. Okay. Remember the reference point was tetrahedral, where the bond angle was 109.5. Okay. Well, what happens is when we start putting lone pairs, like in this case and in this case, that bond angle tends to be crushed in, simply because the lone pairs take up more space. Okay. And when you have two lone pairs, that bond angle really gets crushed, and it's much, much less than 109.5. Okay. This geometry is bent. Called bent. And that's how we use the general formula to determine the geometry and the name and the bond angle. Okay. Now, once you determine how many valence electrons you have for the molecule, that is the number that you have to work with. So you have 10 valence electrons, you got to work with 10 valence. You cannot just magically add more or remove. Okay. So if you don't have enough electrons to fulfill the octet of all of the atoms involved in the structure, that is where you start forming double bonds. Okay. And I'll do some examples of that. And if a double bond does not fulfill the octet, you make triple bonds, and that's the most you can do. Now, after you've done all that, you check the octet, and it's still not fulfilled, then more than likely there's an error in determining how many valence electrons you had to begin with. So go back and check to make sure you are using the correct number of valence electrons. Okay. All right. So let's take a look at an example. This here, we have H2O. Okay. Now H2O is the formula. Hydrogen is the central atom. Okay. So what we do is we go look up the valence electrons for hydrogen. We know that there are valence electrons are 1, but there are 2 hydrogen atoms. So we have a total of 2 valence electrons for all the hydrogens involved. Okay. Oxygen, there is 1 oxygen atom, and it is in group 6. Okay. So there's 6 valence electrons coming for the 1 oxygen. So we have a total of 6 valence electrons, or 8 VEs, valence electrons. Okay. That number that you tally up should be divisible by 2, and that tells me I got 4 pairs. And the reason I do that is because now I can draw lines to represent a pair. Okay, so I got 4 pairs, and a lot of times it's like easier and quicker to just count pairs than it is to count individual dots. Right now you only got 8, makes not much of a difference, but sometimes you could have as many as 32 valence electrons. And there at that point it's easier to count as pairs. So this is the number that you have to work with: 4 pair or 8 valence electrons. You can't subtract more, you can't add more. Okay, you don't have the atoms. Those are what you got to make work. Okay. Now, the fact that oxygen is a central atom, I can quickly write oxygen. And then, knowing that there's 2 hydrogens, I can draw a line for each hydrogen. Okay. And I tend to put them opposite of each other for right now. And it's not going to hurt to put them, next to each other, but as a guideline, just put them opposite of each other. If you had 2 more, I would put them in the 4 directions: north, south, east, and west. Okay. Now that takes care, remember I have 4 pair. Okay. That takes care of 2 pair. So I got 2 pair left to work with. Okay. Now, I cannot put them on hydrogen anymore because hydrogen's duet is fulfilled. That's it. I can't, that's it. So the only logical place to put them is on oxygen. Furthermore, at this point, the way I've written is there's only 2 pair on or 4 electrons total on oxygen right now. So if I add the other 2 pair, okay, so I add the other 2 pair and that gives me 0 pair to work with, I'm done with, okay. I go back and I count, I got 4 lines, which represent 4 pairs, so I haven't lost that. And this is important to do this as you progress because you can, it could end up in a counting error and lose track of the valence electrons you have to work with, or you can inadvertently add more, by mistake. So by doing an inventory as you progress and keeping track of the valence electrons you have to work with, it should work out. All right, so now you go back, and once you're done, you figure out the valence electrons, which is you had a total of 4 pair or 8 valence electrons. So that's good. The octet, everybody's happy. I got 8 around oxygen, okay, and 2 around each hydrogen. So everybody's there. Then I go and I figure out the general formula. And we did this one for water already, and we came up with AB2E2. Okay. B represents the 2 hydrogens, and E represents the lone pair on the central atom. That's important. The lone pair on the central atom. Don't care about any place else, just the central atom. So this then gives us will give us the geometry that we just did with the shapes table. We'll go to the shapes table, look up AB2E2. That tells us we have bent geometry with a bond angle much less than 109.5. Okay. All right. All right. So then we're done. And we got the formula. Now we're going to do a few more here. So this is a small example of how to do this. And there's the geometry and so forth. Here's the picture of it. All right, now let's do these. Okay, we have, granted, you may not know what they are, and that's okay, but you do know that you have the first one, you have hydrogen, carbon, and nitrogen. Okay, it's going to be a fun. All right, let's do that one. Let me get. We got 1 hydrogen. Okay, 1 times 1, you got 1 valence electron. We got 1 carbon, 1 times, now how many carbon is in group 4, right? So you gotta remember that, gotta find a group 4. So that brings a total of 4 electrons from carbon. And then nitrogen is in group 5. So 1 times 5. Okay, so now we have a total of 10 valence electrons, or 5 pair to work with. And that's it, 5 pair. All right, now the central atom has been denoted by the underscore. So we have carbon as a central atom, and then the hydrogen and the nitrogen are bonded to the central atom. So I can very quickly take carbon and then draw a line for the hydrogen and the nitrogen. Okay, well, that took care of 2 pair. So I got 3 pair left to work with. See, that's why I'm keeping track of my valence electrons. 3 pair to work with. Well, I can't put them on hydrogen, so hydrogen's done. Okay, I got 1 bond. So the 3 pair, I can put them anywhere I want now. I can put them on carbon or nitrogen. Now, what I tend to do, just personal preference, is I always fill up whatever is bonded to the central atom, the outside atom. So I'm going to fill up the nitrogen. And so I'm going to go 1, 2, and 3. Okay. So let's double count. Let's double check that we still have 5 pair. I got 1, 2, 3, 4, 5. So that took care of, you got 0 pair left to work with. I still have 5 pair and I'm good to go there. Okay. With far as the valence electrons, I did not inadvertently lose any or add any. Okay. Hope everybody can see there's 5 pair around this. Now, next step, check for the duet octet. Well, hydrogen's taken care of. No problem there. Now let's look at nitrogen. Nitrogen has 8 electrons around it, okay? 3 of them are lone pair, and 1 of them is shared with the carbon, but there are 8 electrons around it, okay? Let's look at carbon. Carbon has 4 electrons around it, okay? 2 and 1 pair is shared with nitrogen and 1 pair is shared with the hydrogen. And so even though the octet for nitrogen is good, it's not good for carbon. Now we can't magically add anymore. So this is where you start sharing electrons with another element. Share with Peter and Paul, right? So what I'm going to do is I'm going to take this pair right here and create a double bond. Okay, which one I take makes no difference, but let's create the bond. So now we have carbon, double bond, H, and then I have my original there, and then my hydrogen, okay? Before I go any further, I double check to make sure I still have 5 pair. 1, 2, 3, 4, 5, so that's still good. I didn't lose any by mistake, okay? Now I go and check the octet. Well, hydrogen we know is always going to be good. Nitrogen is still good, okay, because it has 2 pairs shared with carbon and then 2 pair on itself. So there's 8 around it, it's good. But carbon now went from 4 to 6 electrons around it. Still has not fulfilled the octet. Okay, so what do? We create another double bond. So we're going to take this pair right here on nitrogen and create a triple bond. I meant not another double bond, but create a triple bond. So now I go and redraw it. I got 1, 2, 3 nitrogen, and then 1 line, and then still my hydrogen. Okay, I go back and check. I still have 5 pair. 1, 2, 3, 4, 5. So my 5 pair number I had to work with is good to go. Check my octet. I have hydrogen's good, nitrogen still good, except this time it has a triple bond shared with carbon and a lone pair on nitrogen itself, okay? But that's 8. And carbon now is good with 8 because it has a triple bond shared with nitrogen, that's a total of 6 electrons, and then a single bond shared with hydrogen, 2 more electrons, we have 8. So we got 8 electrons on carbon, 8 on nitrogen, and 2 on hydrogen, and everybody's good to go. So that is our formula. Now we create the general formula. Okay, A represents carbon, and then we have B, right? There's 2 moieties. There's a nitrogen and a hydrogen, okay? Now, we don't have any E's here because E's are only the lone pair on the central atom. Yes, there's a lone pair of nitrogen, but we don't care about that. We only care about lone pairs, if any, on the central atom. So our general formula is AB2. Okay, for this species. So what that does is we then go to the shapes table and look for AB2. And there it is right there, AB2. And you can see the general geometry Here you got the central atom that was carbon, and then you have nitrogen, hydrogen on each side. Its name is linear, and that bond angle is a straightforward 180 degree. It's linear, okay? All right, so. And that's that formula. And you notice there's still 5. I mean, I drew a line for the lone pair of nitrogen. You can do 2 dots, makes no difference. Okay. Let's do the next one. This, by the way, is hydrogen cyanide. Very poisonous gas. Okay. All right, next one right here. We have 1 carbon. Again, 4 valence electrons. Okay. Coming from carbon. We have 1 hydrogen. So we got 1 valence electron. Now the fluorine, we have 3 fluorines, and each one is bringing 7 valence electrons, right? So we have a total of 21 valence electrons coming from the fluorine. So tally that up, I got a total of 26 valence electrons, or 13 pair. Okay, and that is the number I got to stick with. And then since I work with pair, I'm going to follow the pair. If you want to do the single 26, that's fine, whichever works. All right, now let's figure out the formula. So you're given the central atom, which is carbon. And then following that, you got 1 hydrogen and 3 fluorides. So that means that there's 4 atoms bonded to the central atom. So we very quickly can draw 4 bonds and attach the hydrogens and the 3 fluorides. Okay, what that does is you have taken care of 4 bonds. So you want 13 minus 4. Okay, that means I got 9 pairs left to work with. Okay, so they got to be put someplace. Now, can I put them on hydrogen? Can I put any more on hydrogen? The answer is no. Hydrogen is good to go. Let's look at the central atom. How many bonds do we have around carbon? Well, we have 4 bonds. That's a total of 8 electrons. So carbon is happy. I can't add any more. Okay, yeah. Don't add any more because carbon can, sometimes students are not thinking about it and add a pair or something or extra, or take out a pair from an atom and forget the octet. If you count the electrons around the atom of interest, if you see anything less than 8 or anything more than 8, then it's incorrect. The number is 8. Okay, so right now there's 8 electrons around carbon, 4 bonds that are being shared, 3 of them shared with the fluorides, 1 of them shared with the hydrogen. All right, so that means now check for the octet for around the fluorides. Well, there's only 2 at this present time. So they're not, octets not fulfilled for the fluorides. But we have 9 pairs to work with. So we start on the outside and put them on the fluoride. So we go 1, 2, and 3. We can't put any more on this fluoride because it's got 8 around it already. So we continue to the other one. Again, that's 4 around that fluoride. Its octet is happy. And then that means we got 3 more left. So then we put it on the last fluoride. Now we do a check to make sure we are still dealing with 13. So we just did 9 around the fluorides, 10, 11, 12, and 13. So we still have 13 pairs of electrons we are working with, okay? And the octet, everybody's happy. Each fluoride has 1 pair shared with the carbon, and then 3 pair on itself, on each fluoride. So the octets fulfill for them, carbon's happy, hydrogen's happy, we're done. Okay, general formula, we got A, B, 4. There are no lone pair on the central atom, okay, which is carbon. Yes, there's lone pairs on the fluorides, but they are not the central atom. So our general formula is AB4, which by the way will be tetrahedral. Here's AB4 right there. Oh, and it's tetrahedral. There's the configuration. So you can imagine, we got a hydrogen there and then the 3 fluorides around it. Okay, and that's our configuration. All right, and the bond angle of 109.5. There you go. All right, now let's do carbon dioxide, the next one. And we repeat the process. Okay, we tally up the number of atoms that we have times the number of valence electrons each atom brings to the structure. And then we do a total for the whole molecule. So we got 1 carbon at 4 valence electrons, okay? That's 4 there. And then we have oxygens. We have 2 oxygens at 6 apiece. So that is 12 valence electrons. So we have a total of 16 valence electrons, okay? Or how many pairs do we have to work with? You got 8 pair to work with. And that's the number we got to work with. Okay, so let's start building the formula, the structure. So carbon is the central atom, and then the 2 oxygens are bonded to the central atom, so we can draw a line and bond the oxygens to the central atom. Okay, so that takes care of 2, so we got 6 paired left over. Okay, as I stated before, I try to put whatever I have valence electrons on my outermost atoms and work my way in. It doesn't make a difference. You can fill up the center atom with this 8 and then work your way out, 6 1/2 dozen of the other. Okay, whichever one works for you. So I got 6 to work with. I got 1, 2, and 3. Notice I cannot add any more on this oxygen because it's 8. It's 3, 4, 5, and 6. Okay. So now double check to make sure you still have 8. At 6 on the, that took care of 6. I should have 0 pair left to work with. I got 6 on each oxygen, and then the 2 that are shared with the carbon, that is 8. So I'm good to go. Okay. Now we check the octet. There's 8 around the oxygen on the right, and there's 8 around the oxygen on the left, but there's only 4 electrons on the central atom. Okay, so what like we did with the HCN, we start creating double bonds and triple bonds. Now in this scenario, we can take a double bond from 1 oxygen and an oxygen on the left and create a double bond there, and then take a double bond from the oxygen on the right and create a double bond there. So resulting in this structure, C, O, and then the 2 pair, and then double bond O. Okay, so let's double check that we have 8 pair. 1, 2, 3, 4, 5, 6, 7, 8. We have. Let me erase this one here. It came up not too good. Okay. So we still have a pair. So that's a good thing. Okay. Check the octet. Well, the octet on this oxygen on the right, we have 8 electrons around it. Okay. 2 lone pair and a double bond. So we got 8. On the left oxygen, we have 8 around it also. 2, a double bond and 2 lone pair. And then the carbon in the middle has 2 double bonds shared with each oxygen left and right. So hey, it also has so the octet has been fulfilled all the way around for everybody. Okay. And then our general formula becomes AB2. Okay. Which will be the same as HCN, AB2, which, if you recall, was linear and 180 degrees angle. Okay, but you can check that out on your shapes table and you see that. All right. And there's the formula. Now, a note about this. Remember, well, we'll come back to it. Okay. So notice what we've done so far, based on the valence electrons, and given a formula here, we are able to come up with a structure and even a geometry and a name for this geometry. Okay. Now let's do the last one here. We have NH3. And so we have 1 nitrogen. Oh, let me write this up again. Nitrogen. Okay, so it's 1 nitrogen times 5 valence electrons, total 5. We have 3 hydrogens, each one bringing in 1 valence electron, so total of 3. So we have 8 valence electrons or 4 pair total. Okay, nitrogen is the central atom. Okay. And there are 3 hydrogens bonded to the central atom. So very quickly we can draw 3 lines and then attach 3 hydrogens to that. Okay. And so that took care of 3 pairs. So we got 1 pair left. And obviously we cannot put that 1 pair on the hydrogen because the hydrogens are all good to go. 1 bond only on hydrogen. So the only place it can go is on the central atom. Right there. So now that took care of that last pair, 0 pair left. Okay. Go back and double check. Do we still have 4 pair? Yes, we do. 3 pair are shared with those 3 hydrogens, and then there's a lone pair on the central atom. So we still have a total of 4 pair of valence electrons we start off with. Okay. Find its general formula. Well, we have A, B, 3, and then we have 1 lone pair on the central atom. So that's AB3E. Okay. With that bit of information, we then go to the shapes table. And AB, right here, AB3E. Okay. Its name is trigonal pyramid. Bond angle is less than 109.5. Okay, there's that lone pair. This could be nitrogen, and then the 3 hydrogens bonded around it. Okay, and the lone pair on the central atom. That NH3, by the way, that is the structure for ammonia. Okay. All righty then. I'll tell you what. There's a formula. Got somebody knocking at the door. This is what where I went through with respect to HCN. And then basically just went over what I just talked about. Okay. Now what I'm going to do, I'm going to stop it here because the next part of Lewis dot structures has to do with what are called polyatomic ions. And I would direct you to the periodic table on the bottom left corner where you have a table called polyatomic ions. Okay. Some of them are negative charge, some are positive charge, but I will go over them in detail next week. We'll stop it here. And at chapter 7, slide 21. All right. Any questions?